Tierna, is that up okay?
That's it. I can see it fine. Thank you.
Perfect. So, good evening, everyone. You are very welcome, and I'd like to say a big thank you for joining us tonight. The one good thing about Zoom or any kind of online talk is that you don't have to go out in the cold, and I think tonight of all nights we all really appreciate that. So, my name is Kirstin. I am the Science Programme Manager at the Geological Survey of Northern Ireland. Just to give you a little bit of an introduction to the Geological Survey, we are an office of the Department for the Economy, but all of our staff at GSNI are actually scientists from the British Geological Survey. So we are technically seconded to the Northern Ireland government. We have a number of roles. We have a number of work programmes that we work under, including looking at natural resources and the energy transition, looking at environmental change and geological hazards, looking at baseline geoscience and digital data, and also looking at science for society. So under that Science for Society programme, we have got a public engagement role, with the idea being to help people understand what geology is, why we need geology, and how geology benefits every single one of us. And it's under that guise that I am here this evening talking to you all. So I rather cheesily call this talk Rocking Around the Causeway Coast, but it's got the subtitle of the Geodiversity of the Causeway Coast AONB. So what I plan to do is to, first of all, start giving a little bit of an introduction to geodiversity and what it is. I'll then do a very, very quick crash course in geology. And I only do that because it helps everybody who's on the call tonight to understand some of the geological terms, so we're really all on the same page. And then I'll start the main body of the talk. So I'll take you on a geological journey through the Causeway Coast, and I might slip into other bits in Northern Ireland as well, that the Causeway Coast and Glens Heritage Trust still have responsibility for, but are slightly outside the Causeway Coast AONB. So first of all, what is geodiversity? Now, I'm sure most of you in the call have heard of biodiversity, but geodiversity probably not so much. It is a term that is becoming more popular, only because there's a realisation that we need to understand what geodiversity is if we're going to help to protect, conserve and enhance our biodiversity. So geodiversity, if you like, is the variety of non-living parts of our natural environment. This could be rocks, fossils, minerals, soils, landforms, the way the landscape looks. That's all geodiversity. And geodiversity literally and metaphorically underpins absolutely everything that we do, whether it be the material that you build your houses from, whether it be where you build your roads, whether it be the soil that you grow your food in, whether it be the foundations for our built-in cultural heritage. You'll get the idea. It literally underpins everything. So last year, actually it wasn't last year, it was 2022, we had our very first ever International Geodiversity Day, because it's been recognised that we need to really highlight the importance of geodiversity. And it's been, I suppose, described as being biodiversity's silent partner. And those 6 squares on the screen are really just highlighting some of the areas that geodiversity is important for. It's very important for our natural resources that we all know about. It's to say the building materials for our buildings. It's where we get our energy from. But it's also where we get a lot of our water from, and whether it be looking at the shape of the surface, whether it's coming from groundwater. Our geodiversity is very important for our recreation, where we go for a walk, where you might go canoeing, where you might go to ride your bike. It all depends on really what's underneath your feet. And then that leads on to landscape. Our landscape is so important to us, and probably no more so than in Northern Ireland, where we've got some of the most geodiverse landscapes anywhere in the world. It's really important to understand our history, because if we understand about our landscapes, we can understand really how settlements have developed, how our history of, I suppose, people that have actually come to the island of Ireland. It all depends on our geodiversity. And it also helps with our education, helping people to understand where they're living, to appreciate the local community, but also to appreciate the benefits of the environment. And then that leads on to the importance for research. Research in terms of really where our Earth has come from, looking at past climate change, helping us to understand future climate change. So researching geodiversity helps us really to make decisions that are relevant for the current and also into the future. So with that in mind, I'm just going to very quickly talk about Northern Ireland's Geodiversity Charter that the Geological Survey developed with the Northern Ireland Environment Agency. So the Geodiversity Charter is really a set of guidelines on how we can better promote and manage our geodiversity. And the idea is to try and increase in awareness, but also to try and include geodiversity within policy. So this event tonight is really about delivering some of the elements of the Geodiversity Charter, encouraging people to understand the importance of our vast geodiversity. And in fact, the Causeway Coast AONB's management plan is in there as a case study within the Geodiversity Charter, and we will be revising it this year and producing a new one. So we're hoping we can have some more case studies from CCGHT again in there. So look out for that. That'll be released towards the end of this year. So they're just the four main areas of the Charter. I've already mentioned about the policy integration and raising awareness, but it's also about looking at the conservation of our geodiversity and also trying to encourage research as well, because we don't have all the answers. Geodiversity and geology are reasonably new sciences. They're only a couple of 100 years old. And of course, like any science, it changes all the time. So we need to find out more, and we can use our geodiversity here to help us do that. So I'm now going to do a very, very quick introduction to geology. And geology is not something that everybody studies at school. And in fact, we only have one school left in Northern Ireland that teaches geology as a single subject, which is really disappointing, considering the vast array of geodiversity that we have here in Northern Ireland. But most people are taught the basics. So I'm going to really start with the basics that include plate tectonics. So I think most people on the call will have heard of plate tectonics. And the general idea is that the very thin outer layer of our Earth, the crust, is very brittle, and it's broken up into a number of sections that fit together like a giant jigsaw. But those jigsaws don't stay still. Those jigsaw pieces, they move. They move apart, they move together, and they move sideways against each other. And it's that movement that gives us volcanoes and earthquakes. It's also that movement that helps to make vast mountain chains like the Himalayas. And it's also that movement that helps to create new tectonic plates. So, for example, what's happening in Iceland at the moment is a really good example where we have two plates pulling apart, and we have lava that's coming out between there. But what I want to highlight is this map, this plate tectonic map. So you'll see we've got the outlines of continents like Africa and South America, but the thick black lines are the outlines of our tectonic plates. This map is what the Earth looks like today, but over the vast million years of Earth history, so 4.6 billion years of Earth history, our Earth has looked very, very different, and it's because of plate tectonic movement. So we are approximately 54 degrees north or thereabouts of the equator, but we have been in the very far south of the southern hemisphere. We've actually been at the equator, so we are constantly moving, and the same goes for everywhere else on the Earth. So we are very different locations, and it's looked very different all the way through geological time. So that's my first concept, was looking at plate tectonics. The other one is looking at geological time. And geological time was probably the single biggest issue I had when I first studying geology, because certainly as a teenager, Christmas is far away. Never mind 4.6 billion years of Earth history. So it's sometimes really hard to get your head around these vast periods of geological time. But what geologists try and do to try and make that geological time more manageable is to break it up into geological time periods. So the column on the left-hand side is what's known as a stratigraphic column. And if you like, it's if you had stacked all of the rocks from each of the different geological time periods on top of each other, that's what you would get. So the very oldest rocks are at the bottom. They formed during the Precambrian period, and they worked their way up to the very youngest at the top, which is the Quaternary period, the period that we are in now. And the way geologists have worked out the age of those is, first of all, looking at relative dating. So looking at whether rocks share the same characteristics. So, for example, we have got rocks in Northern Ireland that have fossils. So say, for example, somewhere like County Fermanagh, where you've got lots of fossils. We can link them to rocks in Northern England. We can link them to rocks in the United States and in Russia. They all have got very similar fossils, and they all look the same. So we can assume that they all formed at the same time. And that's generally how geological time was first looked at. Now, of course, we use different techniques. We use things like uranium-lead dating. We use other kinds of radiometric dating, so we can get absolute dates to find out how old these rocks are. But really what we do is we find out an age and we assign it to a specific time period. We are very fortunate in Northern Ireland to have every single one of these time periods except for one. So it means we are indeed one of the most geologically diverse places on Earth. And actually, we have the vast majority of those time periods in the Causeway Coast A and B that I'll go on to show you in a moment. My next geological crash course lesson is about the rock cycle. So the rock cycle really works on the assumption that really the Earth is like a vast recycling plant. We have got three main types of rock. We have got igneous rocks. So igneous rocks, that word comes from the Latin word ignis, which means to ignite. So they're rocks that were once molten. So think of rocks that formed from volcanoes, but also we have molten rocks forming beneath the ground that don't actually erupt, but they're all igneous rocks. If igneous rocks are exposed at the surface, they are then weathered. That weathered material is eroded and transported and is deposited as sediment. That sedimentary rock over millions of years is buried and compacted, and it will eventually turn into a sedimentary rock. So geology is not rocket science. So sedimentary rock is a rock that's made up of sediments. So that could be sand, it could be mud, it could be silt, and that would lead to sandstone, mudstone, and siltstone. But it always also takes into consideration rocks that are made up of organic material. So that could be coal, which is made from the remnants of plants, and could also be limestone, which is made up of the remnants of usually dead sea organisms. Sedimentary rocks can then be buried very, very deep within the earth. That can be subject to intense heat and pressure, and they will then change form into a metamorphic rock. So metamorphic comes from the two words meta and morph, meaning change form. And the best analogy I can give you for that is that if you take a cake mixture and you put it into your oven, when it comes out of that oven, it looks very different from when it went in. It's completely changed form, but you're not adding anything, you're not taking anything away. It's just the heat of the oven is changing it, it's changing its composition, and it's changing into a cake. The same thing happens with rocks. So for example, a limestone, if it gets heated up and it gets pressurized, it will turn into a marble. And we get other rocks, for example, mudstone will turn into slate. So you'll see where I'm going with this. We start out with a sedimentary rock, or sometimes an igneous rock, and they can get changed form into something else. They don't melt, they just change form. And that process goes on and on and on. So all the rocks that we see on Earth today are not new. They have really simply been changed or recycled from other material. So I'm going to talk about all three of those rock types today. So you'll hopefully get an idea of why I'm mentioning this. And then my final lesson is just a quick look at geological maps. Now, most of you will have probably seen a geological map. The first thing you will notice is how colourful they are, because what a geological map does is it strips off all of the loose material, whether it be sand, whether it be peat, whether it be soil. It obviously takes off all the vegetation and all the human-made material, and you're left with a bare bedrock. And each bedrock type is given a different colour. So you'll see that in Northern Ireland, we've got a huge variety of different colours, but that's what you're looking at if you look at a geological map. It's different types of rock. Now, sometimes as geologists, we want to look at the soft material on top, but they're not shown on these types of geological maps. This is literally only the bedrock, so the solid geology. So that's your crash course in geology. That took all of 5 minutes. So now we'll move on to the main body of the talk. But before I do, I want to show you this map very quickly. This is a map that was actually produced as part of a geodiversity audit for the Causeway Coast and Glens Heritage Trust. I can't remember how many years ago this was, too many to recall. So it's the reason why I want to show it is just to look at the vast number of different colours on this map. So I'm going to show you this map as we go along our journey, because I want to show you where different types of rocks are formed. But at this stage, it just gives you an idea of the diversity that we're going to look at as we go through our journey and through geological time. So I'm going to start at the very beginning, and I'm going to start in what I call our ancient foundations, and these are our rocks that are Precambrian in age. Now, the Precambrian period really dates from around about 540 million years ago, and in Northern Ireland, the oldest rocks that we have were thought to be around 895 million years ago. But if you want to go right to the very bottom of the Precambrian, we're talking a lot older. So the oldest rocks we have on Earth are around about 3.5, 3.8 million years old. So they're really, really quite old. So what I'm going to do is show you a map. I'm going to show you a map of what the Earth looked like back then. So we think, based on geological information, we can actually work out where different land masses were. And then I'll show you where we were at that point as well. So if you look at the map on the screen, you will see, first of all, there's three things I want to point out. First of all is Southeast Ireland and Northwest Ireland are in very, very different locations. That's number 1 point. So that's a very important concept to think about. Although the island of Ireland didn't exist for a long, long time, the two component parts that went on to make up the island of Ireland were separated for a long part of our geological history. So that's point number 1. Point number 2 is that we were actually in the very far south of the Southern Hemisphere. So if you think about Antarctica, that's where we were back then. And the third point was we were covered in ice, or near enough covered in ice. You'll see that white blob in there, that is an ice sheet. So what do we have from that time in the Causeway Coast AONB area? Well, if you want to look at this little part up here, we're going to look at Tor Head. But a lot of these rocks that are sort of going from the northeast to the southwest in this direction are rocks from what we call the Dalradian supergroup, mostly formed during the Precambrian period. Now, the Dalradian supergroup is a name we give to a group of rocks that formed during this time, and they're called the Dalradian because they're found in the northeast of Ireland and also in the south of Scotland. And as many of you will probably know, the Dalriada were an ancient tribe that really existed between the two areas of northeast of Ireland and Scotland. And they were really a seafaring tribe that really sort of used the sea as their roadways. So they're found in both Ireland and Scotland, so are the rocks, and that's where the name comes from. The rocks that we find from this time period are metamorphic rocks. They're rocks that were obviously started out as something else and have now changed form. And the ones that I want to show you here are actually from Tor Head. So this is you can't see my pointer, can you here? Let me see. Can you see that now? So our Tor Head here is made up of what's called Tor Head limestone. So no surprises that the Tor Head limestone is actually a limestone, and it would have formed in a shallow marine environment, so a shallow sea in the far south of the Southern Hemisphere. And that limestone has now been metamorphosed, so it's actually more like a marble than it is like anything else. And that's really why Tor Head exists, because marble is actually quite resistant to weathering and erosion. So it's a really nice place to go and see some really, really old metamorphosed limestones from this time period. We find very similar rocks on the other side of the Irish Sea over in the south of Scotland, and we can correlate them to being the same as the rocks that we have at Tor Head. So I mentioned that we don't have any evidence of rocks from the Cambrian period, so I can't tell you about any rocks from there. But what I will do is show you our journey as we go along through geological time. So you'll notice that we are in a very different position. The northwest of Ireland is now not that far from the equator. It is part of a bigger landmass called Laurentia. And you'll see the southeast of Ireland is part of this huge continent called Gondwana. And Gondwana nowadays is thought to be made up of parts of Africa, South America, India, and bits of China and Arabia. But obviously they're now all in a very different position than they were back then. So the two halves of the island were separated by a very, very large ocean called Iapetus. And Iapetus is the name in mythology for the father of Atlantis, which is where the Atlantic Ocean gets its name from. So you'll get an idea as to the origins of some of these names. So Iapetus existed before the Atlantic Ocean. As we go on through geological time, the Causeway Coast area does not have any representation of rocks from the Ordovician or the Silurian. They are found in other parts of Northern Ireland, particularly around the South Down Coast, for example. But you'll see we are still moving. Southeast of Ireland is part of a small continent called Avalonia, and it's moving further north. And the Iapetus Ocean is actually getting smaller and smaller. So whenever an ocean gets smaller, we tend to get a couple of things happening. So an ocean gets smaller because one tectonic plate is usually being pushed beneath another one. That's a process called subduction. It's currently happening off the west coast of South America, when we've got one plate being pushed under another. And that's why you get some of the volcanic activity, certainly along the Andes. So that's an example of where that's happening today. But it was happening actually where we now know to be the island of Ireland. So whenever those two plates finally did come together, you find a suture line where that happened. And that suture line actually goes from just south of, it's in County Louth, so south of the border. This is a place called Clockerhead. that goes all the way from the northeast to the southwest to the Shannon Estuary in Limerick. So that line, although you can't see it, it is picked up by geophysical techniques that we use. So you can actually see that. It also leads to volcanic activity, and we do see evidence of this volcanic activity in Tyrone, around Steve Gallen in particular. But you also see it in places like South Mayo and Connemara. If any of you are familiar with Loch na Fui, you know there's evidence of volcanoes that would have been erupting at around this same time. So if we look at this time period, the Silurian and the Devonian, as we move on through geological time, the two halves, what we now know as the island of Ireland, are together, and they're now part of this one continent called Laurentia. You'll see this Avalonia, which is what the southern half is part of, is now crashed into Laurentia, and that's led to this period of mountain building as well. The mountain building, I mentioned earlier on that this is happening in various parts of the globe today, and the most famous is the Himalayas. So the Himalayas formed as India crashes into the Eurasian plate. That's the plate that we're part of. And as if you can imagine, if one plate crashes into another, you do get some crumpling together, and the plate is pushed up as well as being pushed under, and it's led to the formation of the highest mountains on Earth today. Now, this happened as well whenever the two halves of Ireland came crashing together, and we see remnants of this. So I've already talked about the suture line across Ireland, but it's also a suture line between Scotland and England. So we can see evidence of where the two land masses come together. It's also evident in some of the rocks that we find in Norway, and also all the way across Newfoundland on the eastern seaboard of Canada. So we know from that we were connected, certainly the northern half of Ireland, Scotland, Norway, Greenland, and Newfoundland. We were all connected in our geological past. So we do see evidence of this in Northern Ireland. We do see evidence of this in the form of the Sperrin Mountains. Now, the Sperrin Mountains are what I would say are somewhat subdued mountains nowadays. And I only mean that in terms of height, because they're not actually very high at all anymore. They were also part of the same mountain belt that makes up the Appalachians. This isn't a very good image, but the Appalachian Caledonian mountain belt would have been one single mountain belt, and they would have been the same height as the Himalayas, if not higher. But they would have come together around about 400 million years ago, and the weathering and erosion that's taken place since then has led them to look like the mountains that we now see today. Now, you're probably wondering, Kirstin, this isn't part of the Causeway Coast story, so why are you telling us this? Well, it does actually lead us on to the next geological time period that we're going to look at, which is the Devonian period. So the Devonian, this is where we are. So we are around about 20 degrees south of the equator. So 20 degrees south of the equator is approximately desert latitudes. We are very close to the Caledonian and Appalachian mountain belt. And because of all of the weathering and erosion, there's a lot of material that's being washed down from those mountains and it's being deposited. So we see evidence of this, particularly in the areas around Cushendun and Cushendall. So this dark brown and sort of slightly less dark brown around here are evidence of rocks from the Devonian period. This is the most common outcrop. Now, this very dark and brooding picture is one of the ones that was used by Tourism and I for promotion of the Game of Thrones landscapes. So this is known as the Cushendun Conglomerate Caves to geologists. It's given another name by Game of Thrones fans that I just can't quite remember. But if any of you are Game of Thrones fans, you'll know exactly what I mean. So the conglomerate caves are made up of a type of rock called conglomerate, which is essentially rounded pebbles that are held together by a sandstone. If I had to give you an analogy, if you think of a rocky road, Treybake, that's pretty much what a conglomerate looks like. And I know most of my analogies are food, but it'll give you an idea of my train of thought. But this conglomerate is made up of pebbles that would have been formed from some of the material that would have been weathered from this mountain belt. And as it was transported, it would have become rounded, it would have been deposited, and then it would have been covered in sand, which would have held it together to form a solid rock. So if you actually get a chance to go to the conglomerate caves, you can get an idea of some of the pebbles here and see exactly what it's like. This rock is actually a pale reddy brown colour, which is very characteristic of rocks from the Devonian period, and generally gives us an idea that there were desert-like conditions, although this would have been formed in conditions where there was water, because we need water to transport these pebbles. The picture from Cushendall will give you a little bit more of an idea about what this rock looks like. You can see the pale browny reddy colours here. and the small pebbles that lets you know that this is slightly further away from the source, because as rocks travel further, they become more and more weathered and eroded, and they get smaller and smaller. So it lets us know we're a bit further away. So that's our evidence of rocks from 20 degrees south of the equator, whenever we would have been in desert latitudes, and we've got really lovely exposure around Cushendun and Cushendall. So I'm going to rattle on through geological time. I'm going to go to what is my favourite time period, which is the Carboniferous. Now, you'll notice that the Earth is looking slightly different, and we've got essentially one single landmass called Pangaea. Most people have heard of Pangaea. It is the time, or one of the times, whenever we've only had one landmass. Now, I'm talking here around probably about 320, 310 million years ago. In this case, it's part of the Upper Carboniferous. At that time, we would have been just slightly north of the equator, so it would have been quite warm and it would have been quite wet. But there's a couple of things on this globe I need you to just take into consideration. We have another ice sheet. Now, this ice sheet means that we are in an ice age. Now, what an ice age means is that there's permanent ice at one or both of the poles. So for those of you that are quick to think about it amongst you, you'll realise that actually technically we are still in an ice age because we have permanent ice at both poles. But at this time, there's permanent ice in the southern hemisphere. That meant to a dramatic drop in sea level because a lot of the sea ice is caught up on this glacier. So it meant that we are in a terrestrial environment, so we're completely within a landmass. We had a lot of humid conditions, and we had a lot of the development of huge river systems, very similar to what the Amazon river system would be like at present day. So we're talking about tropical rainforests, huge amounts of vegetation, and also huge river systems that would have led to eventually the deposition or the formation of coal-like deposits. So we want to have a look at where these deposits are found. Well, they're actually found in and around Ballycastle. So Ballycastle is famous for its coal mines, certainly amongst geologists anyway, and that's where we have these rocks from the Carboniferous period. So I like to show this slide, and I would in the past, we've done a lot of engagement with schools, but I think this is no more relevant for schools than it is for adults, because this picture is an artist's representation about what the Upper Carboniferous would have looked like. So we're talking about early or primitive tree-type plants. So they're not true trees; they're tree-like plants. So they would have been a bit like some of the New Zealand tree ferns that you can buy in garden centres. We would have had cycads, we would have had club mosses, and all of these would have developed, and we would have had horsetails. So any of you that have horsetails in your garden, and you know how difficult they are to get rid of, rest assured that you nor I will be able to get rid of them anytime soon, because they've been on our planet for over 300 million years. But the horsetails back then could get up to 30 metres high, so you can probably count yourself lucky we've only got the small ones. We also had creatures like dragonflies. Now, this dragonfly, although you can't see it in this picture, is not like any dragonfly you or I know. This dragonfly would have had a wingspan of around about 3/4 of a metre, so they are pretty huge. And this creature here is a centipede, and we would have had centipede-like creatures that would have been approximately 1 to 2 metres in length. And we know this because fossils have been found. So it's not that I'm just telling you something because that's what we think, that's what we know. Now, the reason why these plants and these animals were able to get so big was because the oxygen levels were really, really high on Earth at that time. And that meant that plants and animals grew prolifically. Now, the environment that you'll see here, you'll see there's lots of swampy type environments. So whenever these trees or tree-like plants died, they gathered in these swamps and they couldn't decompose properly. And that over time led to the formation of coal. And it's those coal deposits from the Carboniferous that actually led essentially to the Industrial Revolution. So the coal mines that you know from England, from Wales, from parts of Scotland, from other parts of Europe and from America, they all formed during the Carboniferous period. We also had coal mines in Ballycastle, as many of you will know, although they weren't quite as substantial as some of the ones that they were in England, but they were substantial nonetheless. And it did lead to the development of Ballycastle as a significant town for that reason. So what does that look like in Ballycastle? Well, these are actually layers along the road up to Marconi's Cottage, if any of you are familiar where that is. These layers are actually layers of Carboniferous sandstone. So this sandstone would have been brought originally by rivers as sand, and then the coal layers are actually developed in between. So you can see little bits here, you can see little bits here where the coal would have been developed. The coal layers and the sandstone layers are horizontal, and you will see that they're dipping in towards the land. So whenever they had any coal mines, they actually just dug a horizontal shaft into the cliff, and they were then able to extract that coal. Obviously, the further you went into the cliff, the deeper the coal went. So it was actually more and more difficult to get the coal out as you went on. But nevertheless, it did lead to a significant industry being developed. Just to show you some of the images that we have on our files, this is actually a picture of the Ballyvoy coal mine near Ballycastle that actually only closed in 1967. So, in the grand scheme of things, not that long ago. And this picture on the right-hand side is a gate across one of the abandoned coal mines on that road up to Marconi's Cottage in Ballycastle, where if any of you are eagle-eyed, you'll notice that there are a number of gated entrances to those horizontal entrances to the coal mines. The Geological Survey, on behalf of the Department of the Economy, actually monitors every single abandoned mine in Northern Ireland, of which there are 2,400 and counting. So it's up to us to ensure that these coal mines are safe, and certainly that there is no collapse. And if there is a collapse, then it's our responsibility to come up with a plan on how to remediate that. We have done a bit of remediation work up in Ballycastle in the last couple of years that are associated with the development of certainly some of the caravan parks, where there have been mines or certainly mine entrances discovered. So that's something that we do on behalf of the department. But it's actually very good because it helps us to understand where all the mines are, and then we can actually have a closer examination of how they were worked. So I'm going to move on through geological time. You'll notice my maps are slightly different, but they still show the same thing. So the white outlines are the modern day land masses that you know, but the green outlines are what we think the Earth looked like all those many millions of years ago. We don't actually have any representation from the Permian period, and there's very little Permian rock actually exposed in Northern Ireland at all, but we do have some of the next time period, the Triassic. So the Triassic period in particular here, we're talking about rocks around about 240 million years old. You'll notice that this is us here. You'll see Ireland here. And so just like during the Devonian period, whenever we were 20 degrees south of the equator, we're now around about 20 degrees north of the equator. And that's also desert latitudes. So we would have had rocks that formed in a desert type environment. But just to give you a little idea about where some of those rocks are, they're mostly confined to sort of just north of Larne. So I did say that I was going to stray slightly outside of the Causeway Coast A, and B, and hope you don't mind that, Tierna. But in the interest of telling you a little bit about our geological story, I think it's warranted. But the Triassic rocks are probably best described as being those that formed in deserts and salty lakes. So I did mention that we have a desert type environment, but we also did have sort of restricted, and I mean restricted as in those that don't have any outlet for water. So it'd be restricted inland seas. So any salt water that there would have been from seas, as sea level dropped, as the climate changed, we would have had salty lakes developing. And as evaporation progresses, you get salt deposited, and that salt deposit is then covered by something else afterwards. And that has led to thick salt deposits that have actually been developed primarily in and around Carrickfergus and the surrounding area north of that, and indeed under parts of Belfast Lough. This is actually a picture from the Kilroot salt mine that will give you an idea of the scale of the salt deposits. So I'm not talking about anything that's about 10 centimetres thick. We are talking tens to hundreds of metres thick of salt deposits. Salt is all worked underground, and what I mean by that is everything is extracted and processed underground. The reason for that being is that salt is obviously soluble in water, and our climate does not lend itself to processing salt above ground. Our salt is exported all the way across the island. It's exported across to GB, and it's also occasionally exported over to North America as well. And the majority of the salt you get on your roads. So tonight and the last few days, you'll have seen lots and lots of examples of this. So it will have been from the Kilroot salt mine. So the next slide, this is a very, very horrible looking slide, but I have to tell you, this is probably one of our single most important geological sites. In that picture, you're seeing the boundary between the Triassic and the Jurassic period that comes after that. Now, we know that from looking at some of the fossils in there. So you can't actually see them in the slide. I'll go and talk about this a little bit more in a moment. But the reason why I wanted to tell you about this site is because this is just north of Larne again, on a site called Waterloo Beds. Waterloo Beds is not only an area of special scientific interest, It was shortlisted as being the global stratotype point, and what that means is the place where everybody's referred to globally in the geological community to look at the Triassic-Jurassic boundary. There are a number of these global stratotype sections all the way across the world, just to define certain time periods or certain elements of geological time. And this one was shortlisted. We did lose out to site in Austria, but it is a very important site geologically and scientifically. But it's just to let you be aware of not only are our landscapes beautiful to look at, not only are they beautiful or very, very useful for resources, but they're also very good scientifically. I'll talk a little bit more about another one of those sites later on that is a little bit more beautiful. And that leads us very nicely on to the Jurassic. Now, I've actually put in the wrong map in here. But what this map should show you is the Jurassic period, where we're actually slightly further north, and actually we're covered by a reasonably shallow sea. And that factor is very important because I call this the age of the dinosaurs, and I've been really a little bit cheeky because during the Jurassic period, we were actually covered by a sea, albeit a very muddy sea. Now, technically, if I'm going to get very scientific on you, a dinosaur has to walk on land or certainly live on land. So dinosaurs are exclusively terrestrial, so they exclusively live on land. And whenever I do any kind of event with children and we talk about Jurassic rocks, they ask me where the dinosaurs are. And I always have to say, I'm really sorry, but we've only ever found 2 dinosaur fossils in Northern Ireland. They were found just north of the Gobbins, and it's likely that they were washed in from somewhere else. So we found a thigh bone, and I think we found another bit of a foot of 2 dinosaurs, one herbivore and one carnivore, and they're currently in the Ulster Museum, but we do think they're washed in from somewhere else, and they did not actually live on the island of Ireland as we know it. And that doesn't mean our rocks are any less exciting, because we do have a number of Jurassic rocks. So again, they can be found in some of these areas just north of Larne, but actually the Jurassic rocks underlie a lot of the Antrim Coast Road, which is a really important factor when it comes to looking at geological hazards. So just to have a look at some of these rocks. This is actually Ramore Head in Portrush. This was actually taken very early on a Saturday morning back in October of last year. And Ramore Head is one of the most important geological sites that we have in Northern Ireland from a scientific perspective. So the rocks in this picture are actually Jurassic mudstone. So they would have formed as a result of this shallow sea environment. Excuse me, it would have been quite a muddy environment, and it would have led eventually to the formation of mudstone. Now, this site is known for its ammonite fossils. Now, hopefully you'll see these ammonites. These are the coiled shells of ammonite. This is me looking down on one of those rock surfaces. And this site was the location for a very serious scientific debate whenever geology was first being established as a science. So in the latter part of the 18th century and the early part of the 19th century, there was still a big debate as to how rocks formed. There was 2 schools of thought. There was one school of thought called the Neptunists, who believed all rocks formed from seawater. And there was another group of scientists called the Plutonists, who believed that some rocks actually formed from rocks that were once molten. So a number of very eminent geologists of the time came to Northern Ireland, and they came to Ramore Head, and they saw this rock. And it looks actually not like a mudstone at all. It looks more like a basalt, which is a volcanic type of rock. It's the same type of rock that we have at the Giant's Causeway. And they came to this site and they saw fossils in that rock. And they thought, oh, here's fossils in basalt. This must mean that all rocks were actually formed from seawater. And they thought they'd won the argument. Now, it turns out that upon further investigation, the rocks at Ramore Head are actually underlain by a type of igneous rock. And that igneous rock was actually injected in between the layers of this rock. And whenever it was injected, the heat of that molten rock changed this mudstone to look like it was a basalt. So it was metamorphosed by the heat of the igneous rock. And it was changed characteristic, and it looked like a basalt. It was only whenever they actually went to the Giant's Causeway that actually led to the development of this theory even further, because they were able to look at the columns that formed the Giant's Causeway. They compared them to a place in France, in Auvergne, where they knew that volcanic activity had happened and saw similar rocks, and it actually went on to prove that there were 2 different ways that rocks could be formed. from seawater and from molten rock. So the North Antrim coast, the Causeway Coast A and B, was pivotal in the development of geology as a science. Just to give you an idea of some of the other marine creatures that we have fossils of within the Jurassic mudstones in particular, we've got fossils of these guys here. These are belemnites. Belemnites, as you can probably tell from this picture, are relatives of the modern day squid and the modern day cuttlefish. We see them preserved literally as fossils that look like bullets, but the bullets themselves are actually made up of normally calcium carbonate, or sometimes they're preserved as silica. So they're very, very common in the Jurassic rocks and also in the later Cretaceous rocks. We've also found fossils of marine reptiles, such as this one. This is an ichthyosaur. And an ichthyosaur would be a creature that I would describe as a scary-looking dolphin. It is a reptile, not a mammal like a dolphin, but this would have been a marine reptile that lived in the Jurassic seas. It would have been one of the main predators. We also would have had creatures called plesiosaurs. And if I had to describe a plesiosaur to you, I would say think of a Loch Ness monster, or certainly what people portray as a Loch Ness monster, and that is a plesiosaur. So we have evidence of plesiosaurs as well, normally only as bits of their vertebra or their backbone, but we do have fossils of this. Now this picture is actually from a BBC programme that was done many, many, many years ago, maybe decades ago, a programme called Blueprint. And they went around parts of Northern Ireland and looked at the geology, and then they did reconstructions of some of the fossils and some of the landscapes that existed back then. This is actually from a place called Minnis, which is on the Antrim Coast Road, where there used to be a number of landslides, simply because of the presence of Jurassic rocks that I'll talk a little bit more in a moment about. The fact that we had recurring landslides meant that there was continually new fossil material. And after a particularly bad landslide, it was reported that a skeleton of an ichthyosaur had been found, and it was indeed a full skeleton of an ichthyosaur. So that was removed, taken to the Ulster Museum, and it's now housed there, and it's known as the Minnis Monster. And that's what this reconstruction is actually of. So I mentioned about the presence of the Jurassic rocks on the Antrim Coast Road. So the Antrim Coast Road, most of you will probably be aware of the fact that there is the lovely white layers of the white limestone or the chalk, and above that we've got the black basalt, and it's very characteristic of that coast road. But underneath that white limestone is actually Jurassic mudstone, and the Jurassic mudstone is not particularly competent. And what I mean by that is that, especially after very, very heavy rainfall, as the water percolates down through the rocks, that Jurassic mudstone has got quite a high clay content, and it will absorb lots of water, and it can take on the consistency of toothpaste, which is not ideal whenever you've got however many tons of rock above you. So quite often there will be slippage. So the last couple of months in particular, with a really, really heavy rainfall that we've had, has seen the coast road closed on several occasions. And a lot of that is to do with the underlying Jurassic mudstone that we have along that coast road. This is actually a picture, I think, from October of last year. I actually blatantly stole this off the BBC News website, but it's just to give you an idea about what I'm talking about whenever we talk about the movement associated with the Jurassic mudstone. I'm rattling on through geological time, and we're nearly at the end of our column, but we're now looking at the Cretaceous period. We're about here. We're not too far away from our present location, but the Cretaceous period was known as having particularly high sea levels. You'll notice that parts of Africa are covered in water. This is the period in our Earth's history where we've had the highest known sea level. Because sea level was so high, really everywhere was far away from a landmass, which meant that our seas were very, very clear because there was no deposits or sediments being washed off land masses. The seas themselves were particularly clear, particularly calm, and it led to the development of a lot of cyanobacteria or blue-green algae within the seas. This took the form of a microscopic creature called a coccolith. As the coccolith, as they died and they fell to the bottom of the sea floor, because they're made up of pure calcium carbonate, the calcium carbonate sank to the bottom of the sea, and it gathered at the bottom in really what was like a bright white ooze. And then over millions of years, that hardened to form the rock that we know as the Ulster white limestone, is commonly called the chalk. Now, the chalk itself is again found all the way along the coast road. The difficulty with geological maps is we're only looking at a bird's eye view. And because it's a bird's eye view, we can't always see what there is along the coastline. But the chalk itself is in this very sort of pale greeny colour. So it is exposed in some parts, but it is seen all the way along the coast road. And I'm sure most of you are familiar with it. Our chalk or our Ulster White limestone is commonly seen like this. You'll probably know this is white rocks, and it is literally what it says in the tin. It's a white limestone. We don't like to call it chalk anymore simply because it's compared to the chalk that you get in the south of England, which is actually a very, very soft rock. Our chalk isn't. The Ulster White limestone that we have was actually buried quite deeply after it was deposited, and it's been subjected to a process called pressure dissolution. And what that means is those little tiny bits of calcium carbonate, those little tiny microscopic grains, whenever they're buried, they're put under significant pressure, and at the edges of those grains, they start to dissolve. And because they dissolve, the edges all merge together. And this process called pressure dissolution means that this rock is actually really, really hard, or certainly harder than a chalk should be. So we call it Ulster White limestone. Just to give you another example, this is just down from Dunluce Castle. You'll see how it is exposed at the coast. And actually, considering it is a white limestone, we should actually have a lot more caves and other geomorphological features along the coastline, but we simply don't because our rock is actually really quite hard. This chalk has actually been used for centuries because white limestone is a really useful commodity. So it is still used today. If any of you are familiar with the main quarries like Glenarm, there's other quarries all the way along the edge of the Antrim Plateau in particular that are still working this limestone today. But this picture is actually from just behind Carnlough, from Gortin Quarry. There's a lovely little walk that goes all the way up to the quarry itself, and then up to Cranny Falls. But this quarry, they extracted the white limestone, and they would have then taken it down to the harbour in Carnlough, and it would have been taken over to the Clyde Ironworks, because white limestone was very useful as a flux. So it was used to take out impurities as part of the iron smelting process. And being that the Clyde Ironworks was one of the biggest in the world at the time, there was a significant demand for limestone. But limestone wasn't just taken across for the ironworks. There are so many other purposes. It was used domestically. It was used as quicklime, and it was spread on fields as a fertilizer. It was used as whitewash for buildings. It was sometimes mixed with pig's blood to make pink paint for houses as well. It was used for bleaching linen. So quite often you will see lime kilns dotted around the landscape, and you'll see them in the Causeway Coast A and B as well, where the limestone itself was heated up. The carbon dioxide was driven off, and you're left with quicklime behind, which was then able to be used locally. So there are evidence of this all the way along the coast road. So I'm sure all of you are familiar with somewhere like that. This is just a picture of Carnlough. It's just to highlight how some of the settlements in the area have developed around the geology. I've already talked about Ballycastle, but Carnlough is another example. You'll see that this harbour itself was actually built of white limestone. It'll give you an idea of how competent a rock it actually is, because you couldn't do that with chalk. This harbour was built primarily to transport the limestone across to the Clyde. You'll see the harbour here would have been part of a mineral railway that would have gone up here, would have been across this bridge that if any of you have driven through Carnlough will know, and it would have gone all the way up to that quarry that I showed you a picture of earlier on. So Carnlough, as a village, really owes a lot of its development to the natural resources that were in and around the town itself. And there's just a picture of one of the mineral railways in operation. So this is part of the old Carnlough Town Hall, and that's it there as well, just so you have an idea. Oh. So we've only got a few more time periods to go. We're going to move up to the Paleogene. Now, the Paleogene is sometimes not a time period that people are very familiar with, because the Paleogene and the time period that comes after the Neogene were formerly known as the Tertiary period. That's what I was taught at school. So if it makes you happier, we can call it the Tertiary period, but you'll know what I mean if I do say Paleogene. So we're currently at a very similar latitude to where we are now, or perhaps more towards the direction of Spain, but in the grand scheme of things, we're not actually very far away. We're around about 65 million years ago at the start of the Paleogene period. The North Atlantic Ocean is really just beginning to form. The South Atlantic started to form around about 145 million years ago. The North Atlantic started to form around 85 million years ago. And that process that made that happen was because North America started to pull away from the European and the Asian plates. And that process is still happening today. So up until then, we were still connected to North America. Now, as those two plates started to move apart, it led to the formation of a lot of volcanic material. I mentioned earlier on, this is the same process that's happening in Iceland. And this picture is actually from Iceland last week. Again, one that I took off the web, one of the news periods or the news websites. This is actually a picture from near a town called Grindavik. And just for any of you that are interested, a number of years ago, the Geological Survey, together with the Causeway, Glens Heritage Trust, and a number of other areas, including Iceland, Norway, Scotland, and Canada, were involved in a project called Drifting Apart that looked at our shared geological heritage. And we actually stayed in the town of Grindavik, which is really quite interesting and obviously quite sad for people that live there, in that place is now actually showing examples of drifting apart because the volcanic fissures have just opened. So just to look back on our geological time, here's us here in the island of Ireland. This is Newfoundland over here, and we've got Greenland in between. So what happened about 65 million years ago was that we started to rip apart. The two tectonic plates started to stretch, and as they stretched and they thinned, you get cracks developing in between them, and you get fissure eruptions, and that's what's happening in Iceland. So it's not one single cone volcano, the stuff that you see in cartoons. It's a line, and that line is the crack, and it's up that line that the volcanic eruption happens. So it's not perhaps as violent an eruption as what you might have learnt about at school. It's more of a subdued volcanic eruption. But what it does mean is you get huge volumes of lava that pour out and cover large areas. So that's what's happening in Iceland now, and that's what was happening in this area 65 million years ago. But it's not perhaps as straightforward as I've led you to believe, because there was actually 4 different phases of volcanic activity. It started out with initial, very explosive volcanic activity. One of the best places where you can see evidence of this is actually Carrick-a-Rede. So Carrick-a-Rede, most of you will know, is famous for its rope bridge, but that rope bridge goes across a chasm, and that chasm is only there because it was made up of explosive volcanic material. What happened was there was an explosive volcanic eruption. It ripped through the existing chalk and the existing Jurassic mudstone that's below. That material was thrown up into the air, it came back down, and it was really held together by volcanic ash, which means it's not as resistant to weathering and erosion as the surrounding area. That's why there is that chasm in there, and you'll see little bits of this explosive material as you're going across the rope bridge. You'll see them on this side, and you'll see them on the other side as well. So next time you're going there, try not to maybe think about the rope bridge and what it's built into. You'll see just some really nice examples of this vent agglomerate. So that volcanic activity was very localized. We see examples of it at Carrick-a-Rede. We also see examples of it at White Rocks as well. There's some evidence of explosive volcanic activity, but it was very contained within very small geographic areas. The next phase, however, we can't say the same thing for, because we've got a huge phase of volcanic activity, similar to what's happening in Iceland, where we had huge outpourings of lava that covered vast areas. We've what's called, first of all, the lower basalt formation, and it was made up of individual lava flows. Now, hopefully, you can see some of these individual layers here. Each of these layers, and again, if you're driving up the coast road, this is actually at Garran Point, just north of Carnlough. Each of these individual layers represents an individual lava flow. So just like again is happening in Iceland, you'll have an eruption, then it'll stop. You'll have another eruption, then it'll stop. Because volcanic activity in what we now know as the Causeway Coast area took place over a period of perhaps 2 or 3 million years. It wasn't just one volcanic eruption overnight. So this volcanic activity produced a vast covering of lava all the way across the north of Ireland. Now, it's made what we now call the Antrim Plateau. The Antrim Plateau extends from Belfast all the way up to the north of the Antrim coast. It goes all the way across to Benevena in the west. And it actually goes as far south as Gosford in County Armagh, which a lot of people don't really appreciate. But we do think that this Antrim Plateau was originally much, much bigger. And a lot of the lava has simply been weathered and eroded, and we don't see any evidence of it anymore. So we do think it was huge. So we had our lower basalt formation, and then we had a break. So there was a long break this time, probably around about 500,000 to 1 million years. And then during that time, 2 things happened. Number one was that we got the development of very thick layers of a material called laterite. So laterite is essentially whenever we get deep weathering of basalt. This is the name we give to the lava when it cools and solidifies. The the weathering of the basalt, because the basalt is rich in iron, it tends to lead to a very, very rich iron layer. So a lot of the silica material is washed away, and we're left behind with a concentration of basalt, and sometimes a concentration of iron, and sometimes a concentration of aluminium as well. That was actually exploited for mining purposes that I'll talk about in a moment, but it led to the formation of a particularly recognisable layer called the interbasaltic formation. So it is interbasaltic because after we had the outpouring of the lower basalt, then we had a large break, and then we had another large outpouring of basalt called the upper basalt formation. Now, whenever we had that big break in the middle, I said two things happened with the interbasaltic formation, but we also have the formation of the Giant's Causeway. The Giant's Causeway is not unique. I know a lot of people think that we're the only place in the world that has got these columns. We are not. They have probably columns similar to this on every single continent on Earth. What makes the Giant's Causeway so significant is that if you take it as its full name, the Giant's Causeway and Causeway Coast World Heritage Site, because that whole coastline tells the story of this volcanic history. It tells you about the lower basalt formation. It tells you about the Giant's Causeway formation, and it tells you about the upper basalt formation. It's telling you a story. But why is the Giant's Causeway so localized? Well, what we think happened is that large valleys developed in the area that we now know as the Giant's Causeway. We used to think those valleys developed as a result of weathering or as a formation of rivers, for example. But we now think that was a development of subsidence, or say, for example, some small-scale plate tectonic activity that caused the landscape there to subside and led to the formation of a valley. So we got localized volcanic activity. As that localized volcanic activity erupted lava, the lava pooled into these valleys, and it cooled down very, very slowly. Because it cools down very, very slowly, it gets time to contract, and it contracts generally to give the pattern that we see as the Giant's Causeway, because the cracks themselves develop perpendicular, so at right angles to the cooling surface, and the cooling surface is actually the surface of the lava, so the top of this valley, and that's why they have developed so well. So as anything cools down, it does contract, and that's what's happened at the Giant's Causeway. So it's very localized. It's a very characteristic feature, and of course it's led to the formation of all sorts of myths and legends as well, which also makes this area so special. So I mentioned as well that we had other periods of volcanic activity after that. We had the upper basalt formation that happened. And what we look for as we're going along, looking at some of the geology, is to look at some of the sources of where this lava came from. So we have lots of evidence of volcanic plugs, so areas where the lava outpoured and would have covered the entire surface. Slemish Mountain is a really good example of one of those. So Slemish is the largest volcanic plug on the island of Ireland. It's very symbolic. You can see it very clearly on the road north as you're driving past Ballymena. And it's also, of course, got its association with St. Patrick that makes it even more special. But for geologists, it's very special because it is a huge example of a volcanic plug. And it's probably one of these types of volcanoes that actually fed the Amplin Plateau. So lava would have poured out from somewhere like that, and it would have covered a large area. So I mentioned I'd talk a little bit more about the iron mining associated with that interbasaltic formation. And the area, especially the Mid and East Antrim Council area and the Causeway Coast and Glens Council area, have got hundreds of abandoned iron mines. Some of them dating back to the 18th century, some of them only closing in the early part of the 20th century. I haven't got many pictures of what they're like inside because a majority of them are inaccessible. What I have got, however, is a picture of the one from inside Lyle Hill mine near Temple Patrick that'll give you an idea about what inside these mines were like. Now, one of our jobs, as I mentioned, is to monitor all these mines, and the reason why they're so difficult to monitor is because there's no health and safety considerations, or certainly once they're abandoned, any health and safety considerations that were there have been removed. So you'll get an idea here. These marks in the floor, they would have been actually where the tracks would have been. These would have had the buggies on them that would have taken some of the iron material out. You can maybe see evidence of some of the beams that would have been across the top of the mine, and there would have been vertical supporting beams there too. So this one is relatively safe because basalt is actually a very, very strong rock. So it's a very, very minimal risk of collapse, but we do still gate these all off. And Lyle Hill Mine has actually been used for the filming of a number of movies, including The Vikings, also including Bloodlands, if any of you remember it, with James Nesbitt in it. I was also used to film a couple of horror films. And one time whenever we were up there inspecting the mine, we'd forgotten that the remnants of this horror movie had been left behind. And tell you, that's not exciting, not that funny to see whenever you're looking at it with a torch. But thankfully it's now been removed. There's evidence of these mines in the landscape as well. So this is up near Portmore Forest. This is a picture from one of our drones. These are actually spoil heaps in the mines. Huge amounts of iron were taken out of the mountains on the hills in behind Carnock and Ballygally. Again, taken over to the ironworks in Clyde. But you just see very few remnants of them except for things like this. And then this is actually a sculpture up at Glenravel, sort of indicating some of the industrial heritage that landscape used to support. And in our very final time period, this is the time period that we are now in. This is the Quaternary period, and most people associate this with the what people often call the last ice age. I don't like to call it that, as I mentioned earlier on, because we're currently still in ice age. But what I will talk about is perhaps the last glaciation, because in our current ice age, we know we've had between 20 and 30 different glaciations. And what that means is that the ice sheets grow big enough to actually cover us. So in the last glaciation, ice would have grown from the North Pole, it would have travelled southwards, and it would have covered the entirety of the island of Ireland and probably the majority of Great Britain as well. I'd rather, again, cheekily use this image. I don't have a map for this one because the Earth is the way it is now. So I haven't used a map. But this is really an artist representation of what the ice age would look like. But of course, it wasn't like that all the time. It wasn't always covered in ice. Sometimes it was frozen ground. Sometimes there was minimal vegetation. But again, it's just to give a little bit of an idea and to paint a picture in your head. So what I have done is I've got a view, if you like, of the Northern Hemisphere. We've got the Arctic Ocean here. We've got the present ice cap, although this was done a few years ago, so it's probably very different now. And then we've got the ice cap around 18,000 years ago. So you'll see the extent of the ice cap. You'll see that it did cover, we now think it covered the whole of the island of Ireland, not just down to the far south, but I'll just give you an idea of the size of it. The ice, it was easier for the ice to grow over land than it was over sea, which is why you've got some of these gaps. So it'll just give you an idea. And then we've got some pictures from various glaciations just to let you see where some of the ice came from and where it went to. So in Northern Ireland, we had a build-up of ice in the area that we now know as Lough Neagh. The reason why it built up there is because it was a depression. And as you get snow falling and building up, it actually ended up building momentum and then travelling, radiating outwards and would have formed lots of glacial features. And this is actually a later stage in the ice age, and you'll see that more ice movement came. But one really important factor I want to point out here are these green arrows. These are Scottish ice. So the ice that would have led to a lot of the features we find on the Causeway coast would have been actually as a result of Scottish ice. As it travelled from Scotland, it travelled from the northeast, and it travelled to the southwest. So that's what's led to a lot of the features we see in the landscape. One of the most, the easiest probably to get across would be the Glens of Antrim. The Antrim Glens were all formed by ice, and it would have all been Scottish ice that would have moved up the valley, not down the valley, which is how we normally think of it when it comes to water. But the ice would have actually gone up the valley. We know it's ice because of the shape of it. River valleys tend to be V-shaped, and the rivers occupy the bottom of those valleys. Ice valleys tend to be very wide. They are U-shaped because only something as powerful as an ice sheet can remove that amount of material. The way ice sheets work, if you like, I would describe them as first of all, like a giant sheet of sandpaper, because as they move, they actually pick up bits of material. Those bits of material are then really stuck to the bottom of that ice sheet. It could be bits of rock as small as your fingernail, as small as fragments of sand, but they could be big boulders that sit the size of small cars. And as they move along the landscape, they either can abrade the surface below or they can pluck bits out. The best analogy I can give you for how ice plucks material, because you wonder how does it do that. If any of you have ever been to the freezer to get an ice cube out and it's stuck to your finger, what's actually happening is that ice sheet is actually, or that ice cube is momentarily thawing at its edge and then refreezing with your finger in it. That's why it sticks. The same happened with ice at the base, because it becomes slightly melted at the bottom and then it refreezes as it moves with material in it, and it can rip out huge bits of material. So that's how the Glens of Antrim formed. Once the ice melted, we were left with other types of landscape features, because what happened to our landscape, if you imagine the huge amount of pressure that is exerted upon the surface of the earth because of ice sheets, it pushes the earth down. Now, it takes a while for that landscape to readjust. So what happened is that as the ice melts, sea level rises really, really quickly. So the sea level will actually be very high for a period of time. The Earth, however, takes a little bit of time to readjust, and it's still rising today. So this is actually a picture from Ballantoy. This is the sea cave, but you'll notice there's no sea beside it. So this cave would have formed as a result of weathering and erosion, as a result of sea activity. But because of this readjustment after the ice has melted, the sea cave is now high and dry, but it would have originally, at the end of the last glaciation, it would have been at sea level. And then one of the other features that we find as a result of some of these ice sheets melting is that we have some kind of collapse. And the collapse happens generally along the edge of the coastline. And this is an example of Garran Point, where we have a lovely example of what's called rotational slip, because these blocks have rotated as they've slipped downwards. And this is the examples we're always given in textbooks, is Garran Point. And again, leaving their impact on the landscape. And I'm going to finish there, because I think we've gone on our journey, basically going from really the Precambrian period. We're talking probably around about 550 million years ago, right up to the present day. So hopefully it'll give you a flavour as to the geodiversity of the Causeway Coast and a little bit beyond. And I'm happy to answer any questions if anybody has them.